Welcome. Let's go ahead. We are concerned about multiple integrals, you could say, as a general term. So, but as always, there's not simply one sort of multiple integral. Instead, there are very different concepts about it, and I will do my best to try and explain what's the difference. Well, this one is actually quite simple as far as the target is concerned. The target is just to calculate the area of an ellipse, which you all have a concept about. Okay, so the ellipse as a very well-known figure, a planar object similar to a circle. You could say the ellipse is, simply speaking, a circle that has been stretched or squashed in one or even another direction. As long as we do not introduce sort of a rotation, it's relatively easy to write down the equation of such an ellipse. And this is what you see here. It's quite a famous equation, actually, and it resembles the circle equation, which you all know, especially the equation, the famous equation of the unit circle, which would look like, well, here it's already in transformed in the version transformed to new coordinates. But as you know, usually we write down x squared plus y squared equals 1, which is the equation of the unit circle. And now you may easily imagine that by dividing the x coordinate squared using a certain positive constant, a squared, and then also adding the squared version of y, also scaled, which means stretched or squashed, using another positive factor. Here it's called b squared. So this is an explanation for this to be the unit circle transformed to an ellipse. Okay, so this is the general ellipse equation as long as you do not introduce some kind of rotation. Okay, so if you do so, you would introduce some mixed terms like x times y, etc. But this is not the case. So the idea is just to set up a double integral. Of course, we need a double integral in order to, well, just to get along the whole area here. And if you remember the previous exercise, well, this was a little different, but also here we had certain, oh, sorry. Yeah, I wanted to show this here. Right, we had this so-called disk. This was just an application example, but anyway, we had a certain area in the xy plane which we had to go through. We had to go along this disk in order to sum up this surface mass density to calculate its total mass. So, in a more purely mathematical sense, it's often the case that you have sort of such a bottom area, and then you construct in the z direction, which points towards you, you construct a three-dimensional body, and then the task of this double integral would be to calculate the total volume of this body. So this is usually the original setting where you learn how to do it. And I'm quite sure that your lecturer used such a three-dimensional geometrical example to introduce the topic. And that's why I did the same here. Look, just imagine this would be our ellipse in the xy plane. This is, of course, this is a perspective view. This shaded area would be our ellipse, and we are interested in its area. Now imagine you would construct a three-dimensional body which has a constant height of 1, as you see here. So this would immediately mean the volume of this, well, let's call it, how should we call it? It's sort of an elliptic cylinder. The volume of this object would be exactly its bottom area. Why? Well, simply because it has a constant height of 1. So why I'm giving you this sketch, the reason is simply for you to imagine what we're doing here is calculating the volume of this object, but at the same time calculating the bottom area. So you can also leave this away in your thoughts. Just throw it away. It's also possible, look here for a moment, to say what we want to do is calculate the area of the ellipse by just summing up differential area elements by carefully, going along the whole bottom area. So that's the task actually. And you know that sometimes I use a simple integral sign, even if it's a multiple integral I'm calculating. So this is what I do sometimes, and other times I use double or triple integral signs. Both methods are officially allowed. Well, you should always look at the differential. If the differential is an area differential, you can conclude by context that this has to be it has to be expressed as a double integral. If this were a volume differential, then in this case we would even need a triple integral. And we will have some examples, at least one or two, where we need a triple integral. Okay, so take this just to be symbolic for whatever it is. Okay, so now let's start. And the idea is, and this is also sort of a hint, we should use the transformation which is given here, which says that x equals a constant times u and y equals b times b. Now, and then afterwards even use polar coordinates. And the reason for this is rather simply the fact that it's not so easy to handle such an area in Cartesian coordinates. It's much easier to set up a so-called type 1 area even with constant limits by transforming to polar coordinates. You will see. So what I give you here is that, honestly speaking, it's the coordinate transformation, yes, but more precisely, it's the coordinate back transformation. Why am I saying so? Well, look here. You have two equations which tell you how to get your old coordinates using the new ones, right? So, and also, side remark, it's quite a simple transformation, of course, because it's simply, stretching or squashing your coordinate system in a way along the axes so that you transform this ellipse to formally, you transform it to a unit circle. That's what we do, actually, okay? So, and the simplicity here lies in the fact that the x coordinate just depends on u and not on v. It might depend on both. Also, y might depend on u and v, but it doesn't. It just depends on v. So that's a very obvious reason for this transformation to be one of the most simple transformations in the world. Okay, so please don't be in any way upset about this. So what we're doing here is we just rescale, or you could, so we do a rescaling, but this equation tells us how to get the old variable expressed by one of the new variables, and also here. So, but that's a clear setup, and now just let's use it. The question is always, what does this transformation mean? Or in other words, what does this transformation imply for the differential area element which we need inside our integration? So is the differential area still the same? Of course it isn't. So what has this been originally? Differential A, it has always been dx times dy. That's simple because we are using Cartesian coordinates where the axes are perpendicular to each other and so on, okay? And scaled naturally. So now we have to ask the question, what is the differential of the old variable x in relation to a differential of one of the new ones? in this case, we just have a dx over du because dx over dv doesn't make sense. Well, it makes sense, but it would be 0, okay? So the answer is simple. Taking x as a function of u and v, but actually just a function of u. Well, differentiating x with respect to u, and the result will be constantly a. So that's simple. Also, y differentiated with respect to v, so in other words, dy over dv will be constantly equal to b. That's it. Now, it means by splitting up the differentials that any incremental increase of variable x will always be factor of a times incremental increase of u. The same holds for y accordingly, okay? dy will be equal to b times dv. So that's, as I said, simple. And now inserting this substitution or transformation into our equation, it gives us, look here, I just put this x over a in parentheses, then square, and x over a, sorry, equals u, of course, by this transformation. Also y over b equals v, and this means my equation transforms to be u squared plus v squared equals 1. And now we have, in the new coordinates, we have the famous equation of a unit circle. So that's really, I can even give you a sketch of this. Just imagine, this is our ellipsis in its original view. And then introducing this transformation in a new coordinate system, which is called uv, which is still Cartesian in a way, in a sense, right? At least it's still perpendicular, referring to the axes. We have a stretching or squashing procedure inside which transforms our ellipse to a unit circle. So here it is. And now, combining these two differentials by multiplying them, we get a new expression for our differential area, which is then a times du times b times dv. And for rearranging these terms, we get a times b times differential u times differential v. And now, although it's very simple, this is probably a good opportunity for you to understand what this famous Jacobian determinant always means. This is a very powerful instrument introduced by Jacobi, which tells us that the determinant of a certain matrix, which is closely connected to any coordinate transformation which we perform, is what we need to transform our area element to the new coordinates. So I call this J1, J for Jacobi, J1 with these determinant bars. Okay, so and I guess you know this, how to set up the Jacobian. You just take your old variable number 1, and then you place the partial derivative with respect to the first of the new variables here. And then you go on in this row, keep using your first of the first one of your old variables, and then take the partial derivative with respect to the second new variable. The same holds for the second row. Then here I proceed to old variable number 2, which is y, and then I take the partial derivative for u, for v, and that's it. And now you see what I get is simple in this case, because we have found out that x over, well, let's say differentiating x for u gets us a. So this is what I write here. And you please note, this is the partial derivative of x with respect to u, although x does not even depend on y, does not depend on v. It might also depend on v, and that's why we have to take the partial derivative. But in this case, the partial derivative is identical to the regular derivative, just for your, for your comfort to understand why I'm writing it down this way. So it's a, but x partial derivative for v, of course, gets 0 because x does not depend on v. The same is true for y. Analogously, we get y index u equals 0 and y index v equals b. Now, the determinant of this, of course, is take the diagonal product, which is a times b, minus the second diagonal product, which is 0. So that's just, well, you could say confirmation of the fact that this factor of a times b has to be included when solving an integral in order to to calculate something which is related to the original coordinate system, but using the new coordinates. I hope you understand what I'm saying. Now, in these new coordinates, our ellipsis gets transformed to be the set of all pairs of u and v, which fulfill now, of course, u squared plus v squared lower or equal than 1. That's clear. We see it here. And still, this is not what we need to perform our double integral. We have to, well, we might do everything in one step, but I decided to separate it, okay? So this was a little first transformation, and we just take a second transformation right after, which is the following. And this should be familiar to you because it's the usual planar polar coordinates which I'm introducing here. So now I say my old, meanwhile, this is an old coordinate, this also, okay? They have been new, but now I call them old. The old u equals nu r times cosine of nu phi. So r and phi are our new coordinates now, introducing polar coordinates. And of course, the horizontal coordinate will be radius, distance from the origin, times cosine of phi. You know how phi is defined, as you see it here, for any point P. For example, here in the first quadrant, you get the distance from the origin as variable r, and the angle to the positive first original axis as this so-called, well, let's just say angle phi. Okay, so, and v equals r times sine phi. That's nothing new. We've been using this all the time. Now, again, the question is, what is a differential area element dA, which is still equal to dx times dy, and this means it's also equal to ab times du times dv. But what is it expressed by the new variables, by the brand new variables r and phi? And it turns out that here we need another, let's say, correction factor of radius r to replace this by radius r times dr times dv. Well, the reason for this correction is actually that while the variable r is a pure, let's say, distance variable as usual, the other variable phi is not. The phi variable, as we all know, is an angle also in radians measure. So it's not even a distance. And in order to transform this differential increase of angle phi to a real distance, we have to multiply it with the distance of the point, the respective point P, for example, the distance from the origin. So in the end, what we get is now differential area A equals AB times R times dr times d phi. And if you want to be sure about this factor of R, it's also a good idea. Well, I call it du. I should call it, I'm not sure. I tried and should say J for Jacobian. In German, always, most of the time, we are using D because, it stands for determinant. Well, anyway, I call it J. And now the determinant of the Jacobian, of the total Jacobian of this double transformation will be, oh no, sorry, this is the second part. Okay, let me just call it J2 at this point and take this away. Sorry, J2, okay. So anyway, what we get here is setting up the second Jacobian, which now means we have to take the partial derivative of old variable u with respect to r, then with respect to phi, and the same for v. So now look here again, taking the r derivative of this term, keeping phi constant, gets us some factor cosine of phi, which stays there, times r differentiated for r, so that gets simply cosine of phi. Second, partial derivative for phi, factor of r this time stays there, and then cosine of phi gets differentiated to be negative sine of phi. So this is nothing new, I suppose, but okay, anyway. The same for phi, for v, v index r gets us sine of phi, and v index phi gets us r stays there, times derivative of sine of phi for phi, so cosine of phi. And now taking the determinant, this is the diagonal product, which gets us r times cosine squared of phi, plus now the negative, the second diagonal product has to be subtracted as always. So we have to subtract negative r times sine of phi times sine of phi, we get plus r times sine squared of phi. We can pull out or draw this factor of r, this common factor outside, and put squared sum of phi in parentheses. So this is a factor of 1, and all that remains will be r, simply r. And that's what I used here by just geometrical considerations. Okay, so just for your information, the combined Jacobian may also be taken, so sort of just performing all we've done in one step, which would mean that x of r and phi equals a times r times cosine of phi, and y of r and phi equals b times r times sine of phi. So this would be the total coordinate transformation that we need to do this. And well, it's called d again here. I will replace it by j, j, well, let's say j total, okay. And also, of course, the determinant of the Jacobian will be a, b, r. So that's what we get all together as it's written here. You see, putting up the Jacobian of this transformation gives you a, b, r as in one step. Okay, anyway, now we are prepared to set up our double integral as an iterated integral, by the way. So the area of the ellipse will be integral over its bottom area, and simply those differential elements dA. So what we do here is just we continuously sum up differential area elements over this whole bottom area of this ellipse, which then gives us the total area, which is covered by an elliptic curve. And that's what we want. So what is it? Now, it will be, of course, a double integral, or more in detail, it will be an iterated integral. And we have to find out which are the limits for our integrations. And if I decide to integrate over phi first and then over r, which I do here, you see it looking at the differentials, I must convince myself that it's necessary to have phi increase from 0 to 2 pi. Why? Because this is just once around. You see it here. I start here, you could say, and then I let phi go counterclockwise once around from 0 to 2 phi. This is just one rotation, but at the same time, I must increase my radius variable starting in the origin from 0 to, now I'm here in my thought, from 0 to the radius of my, well, you could say transformed ellipse, because in this way the radius varies dependently on the direction. But as you know, we have firstly stretched and squashed this situation so to have a unit circle, and now this time the argument goes to increase r from 0 to 1, actually, because our ellipse is, if you want, it's not an ellipse anymore, it has transformed to be a unit circle. Okay, so that's why I write down r equals 0. R starts from 0 and increases up to 1. Well, always thinking about this sketch here, this situation expressed in polar coordinates r and phi. So you will agree with me that the radius variable, after having transformed to u and v, will increase from 0 to 1. Okay, so that's it. And now we have this Jacobian inside ABR. That's important. But then we have to integrate over phi, which is simply because this is constant. It is not dependent on phi. You know that we have to treat this as to be constant, leaving r alone. So it means we get a linear result, or we can also say, since this is just a differential over which we sum up, we just get a factor of the interval, which is a factor of 2 pi for this part. Also, before I do this, I just took this ABR one step to the left, because it simply doesn't depend on phi. And here you can see even better that the result will be simply the factor of 2 pi of this phi integration. And then after drawing this outside, 2 pi times AB, AB is constant, I can also draw it outside of the integral. Then what remains is just an integral from 0 to 1 of r over the r. And this, of course, gets us the primitive function r squared half, which is then to be evaluated from 0 to 1. So just inserting 1 for r now, I get a 1/2 contribution minus 0 at the lower bound. And that means I get 2 pi AB times 1/2, which is simply pi times A times B in the end. And this is really a nice result, because if you, in case you didn't know it, it's very similar to the well-known formula for the area of a circle, which is pi times r squared. And now our result is that by stretching or squashing a circle along one or both Cartesian axes, it transforms to an ellipse which has an area similarly to the circle equation here, by replacing one of the r factors by the so-called, you know how it's, what it is? It's sometimes called the, the major semi-axis A and the minor semi-axis B, these two. So usually you take the larger one for A and the lower one for B. It can be the other way around also. But anyway, this is what you get. You get pi times the product of the semi-axes of the ellipse as its area. A little add-on just for your interest. Of course, it's interesting to ask for the perimeter of an ellipse also, perimeter or circumference, however you call it. And this one, this is a German symbol for Umfang. And it turns out it might be, similarly to here, it might be sort of, you know, looking at the circle equation, which tells us that the circumference equals, well, let's just call it P for perimeter. Now, for the circle, we are all informed about this P equals 2 pi times R, you know what I mean? So this is sort of 2 pi times I, sorry. So this is pi times how do we say, the diameter of the circle, right? 2 times R would be the diameter. And now you might have the idea that in the case of an ellipse, you would have to just add the two semi-axes. A plus B, this would be similar to 2 times R. So this is a nice idea, but quite shockingly, this is not true. The answer to this question is we don't know. From a mathematics point of view, it's a fact that the integral, which you may set up, by the way, would be sort of a certain path integral, as you remember, just for sort. Did I write it down? No, I didn't. Well, it would be sort of integrating along the curve, you know, and then just adding differential, radius vectors. You remember, this is sort of a path integral to just calculate the length of a curve. Anyway, you can set it up And this leads you to a so-called elliptic integral, which is provenly not analytically solvable. So this means we will never know exactly what the parameter of an ellipse is. On the other hand, for an engineer, this just doesn't matter, because he says we can use any approximation which is arbitrarily exact. But, well, it's interesting from a mathematical point of view that this is not analytically solvable. But we solved our exercise and calculated the area enclosed by an elliptic curve in the two-dimensional vector space.